Hello, everyone. Thank you for joining this evening's fourth KSEA Distinguished Guest Series. My name is Young-Ki Kim. I'm professor of physics at the University of Chicago and president of the Korean American Scientists Engineers Association, KSEA. Artificial intelligence, AI, is transforming the world. AI coupled with promising machine learning techniques is broadly affecting many aspects of our many various fields, including science, technology, industry, and our day-to-day life. With this evening's event, I hope we'll have a chance to learn about AI and its recent advances and applications. I'm very pleased today that we have two internationally renowned experts in AI, Professor Dongyuel Lee and Professor SueYeon Chung. And let me briefly introduce them here. Professor Lee is the Tisch University Professor in Electrical and Computer Engineering at Cornell Tech, and Executive Vice President and Head of the Global AI Center for Samsung Research. He received his BA in physics from Harvard University and PhD in condensed matter physics from MIT. He was a researcher at Bell Labs in the theoretical physics and biological computation departments. He's a fellow of the IEEE Institute of Electrical and Electronics Engineers, and this is the world's largest technical professional organization. And he's also a fellow of Association for the Advancement of Artificial Intelligence. He has received the NSF Career Award and the Lindback Award for Distinguished Teaching. He was also a fellow of the Hebrew University Institute of Advanced Studies in Jerusalem and an affiliate of KSEA, the Korean Advanced Institute of Science and Technology. His group focuses on understanding general computational principles in biological systems and on applying that knowledge to build autonomous systems. Professor Chung is an assistant professor in the Center for Neuroscience at New York University and a project leader at the Flatiron Institute. She's also an affiliated faculty member at the Center for Data Science and Cognition and Perception program at NYU. Prior to joining NYU and Flatiron, she was a postdoctoral research scientist in the Center for Theoretical Neuroscience at Columbia University. Before that, she was a fellow in computation in the Department of Brain and Cognitive Sciences at MIT. She received a PhD in applied physics at Harvard University and BA in physics and mathematics at Cornell University. Her research interests are at the intersection of computational neuroscience and deep learning. Her group focuses on understanding computation in the brain and artificial neural networks by analyzing the structure of information processing in neural networks and developing neural network models guided by neuroscience. To do this, she uses the tools in statistical physics, machine learning, and applied math. So concerning the format of today's program, we will start with the presentations and remarks by our two distinguished guests for about 20 minutes or so. Then we'll receive the questions from you. And we will end with an online raffle. So please join me in welcoming Professor Lee and Professor Chung with a big round of applause.
Thanks, Young-Ki. Thanks, everyone, for joining us tonight. SueYeon and I, we're happy to share our thoughts in terms of what's happening with AI and in terms of trying to understand, where intelligence is going and trying to understand what's actually happening inside our brains as well. So what we're going to do is begin with some introductory presentations to give you some background materials. And then we'll open up the floor for questions and discussions for the remainder of the hour before the raffle. So let me start by trying to share my screen. Hold on one sec. Okay, I think hopefully everyone can see that. Great. Okay, so as Youngki mentioned, myself and SueYeon, we've been thinking about AI and kind of how we can understand the brain in kind of in parallel context of natural intelligence versus artificial intelligence. And we wanted to share some of the historical perspectives as well as some of the recent research going on in these fields. So to begin with, I think, for me, AI has always been an exciting area of research and to think about. I remember, my inspiration to do scientific research was, back when I was a child. I think the first movie I saw was Star Wars. And, in Star Wars, you see these amazing robots, C-3PO there in the middle, along with R2-D2. And I remember, as a kid watching this and thinking, I don't know, is this really possible to build something like this? Where, if you remember, C-3PO is actually a linguistic robot. He could actually speak multiple languages and was translating between all the different alien species and humans. And so, is it possible that you could really build a computer and a machine that could understand language and be able to translate and to, do these kind of amazing things? And as you see now, it is possible that AI has gotten to a point where, what was just fantasy fiction in the movies has become reality today. And this is true, throughout many, many years of Hollywood filmmaking, right? I don't know how many people here are science fiction fans, but, going back to HAL in 2001, A Space Odyssey by Stanley Kubrick, the Terminator series, these are evil kinds of forms of intelligence and robots. WALL-E, which is, Disney's take on AI, and Baymax, these kinds of characters that have been always, I think, inspirational for even kids to think about, where science can go and what kind of wonderful kinds of creations can you make from science and engineering. So I think this to me has always been the inspiration for, trying to better understand ourselves through trying to build these types of systems. And one way of trying to measure the progress of how far we've gotten with AI is to try to compare ourselves with AI, right? So kind of man versus machine contests. This has a long history going back to the late 90s, where we had, Western chess, where IBM built a computer back then, which beat the world's best human chess player, Garry Kasparov, at the time. And this was, seen as kind of one milestone of AI, that, you could have a machine beat you at chess. Now it's a given that if you even play, your handheld phone to play chess, you're never going to be able to beat, your phone in chess. I mean, this is where we've gotten to. More recently, we've had computers playing, trivia games like Jeopardy, right? This is a game show where you have to be able to answer questions about different types of knowledge. And so, we saw that we were able to have a machine beat the world's best humans at that. And then more recently, I think what created a lot of excitement over AI was that DeepMind built a computer called AlphaGo that went to Korea actually and beat Isedol at that time back in 2016 at the game of Go. And this was seen as a huge milestone for AI because, when they, back in the 90s when AI beat Garry Kasparov at chess, at that time the experts were saying, well, maybe they can win at chess, but they'll never win at Go, because Go has so many different possibilities at each move that the branching factor of the game, the number of possible games, is so much larger than number in chess. And the idea was that, computers would never be able to kind of handle that huge explosion of different types of moves and possibilities. But we see, from 1997 to 2016, that's less than 20 years, that AI has advanced to a point where it was able to basically beat humans at Go now. So this is kind of an interesting reflection of ourselves, right? And it spurred debate about whether AI is going to get to a point where it achieves kind of superhuman status with all these kinds of intellectual pursuits. And that's kind of an interesting debate is, what is the limit, right, to AI in terms of getting better than humans? So as I said, throughout the ages, people have been interested in AI, and kind of the approaches have changed scientifically over the decades. So just to recap kind of what's happened over the years, back in the 1980s, there was a lot of interest in kind of the first form of artificial intelligence. And the way that AI worked back in the 1980s was based upon rules and logic. And so you would have human programmers, human experts, try to write down the rules of how they thought. For example, they would make rules like if you go outside and you see a cloudy sky and there is water on the ground, then it probably rained, right? It did rain last night. So these are kind of the rules, these kind of hard-coded logical rules that you would then try to program into a computer. And then basically using all these rules and observations, they were trying to build these expert systems that would, try to reason about the world. Now, this was a good idea, but the problem was that it's almost impossible to write down all these rules, and it's very brittle, right? That a lot of times we're not certain about whether this should be the case or not. And so what happened was there was a lot of hype back in the 1980s about AI being able to do things like make medical diagnoses at that time, or to be able to do, predictions. And it didn't really work well. And so what happened was that in reaction to that, there was in the 1990s, the early part of the 1990s, we had what we called the AI winter. And what we meant by winter was that, there was no food, there was no funding for AI at the time. All the scientists and people who were working in this field then switched to other fields because it was thought that this was a dead end. And so only a few very dedicated people were then working on AI at the time. And these are the people that really believed in it, thought that it could be improved. But at that time, everyone else was saying, no, it's impossible to do. Don't worry about it. And so those small number of people then started to develop the field, going from rules and logic into the 2000s into a field called machine learning. And the idea here is instead of having a human try to write down all the rules about how to think, what we wanted to do was have the computers just observe from data, looking at the statistics of the data and being able to make up its own kind of observations and reasoning from the data itself. And this is, machine learning or statistical machine learning was then being developed at the early part of the 2000s. And to be able to then make classifiers or regression machines that would basically learn from data. And then what we then saw was in, the latter part of the 2000s, the beginning part of 2010, was a revolution in machine learning using a certain type of model called deep neural networks. And these are, neural network models that tried to replicate what neurons in the brain did to a certain extent, but then train these neural networks using lots and lots of data. And using lots of data, we're able to then train very deep or larger networks that could then model the data very efficiently. And that's what has really led to this kind of new wave of AI today, using these neural network models, using lots of data to be able to then model things that we have around the world. So that's really been how we got to this point today. But, it's kind of inspirational that, that this started back in the 1980s and 1990s through a group of dedicated scientists and engineers who believed in the fact, even though, it seemed like it was an impossible task at that time. So, I think the lesson here is that you should never say never, and to, work in science and engineering that, it is possible, even these kinds of incredible things. It does take some time. It takes research, but it takes smart people to be able to build these things. So that's a brief history of what we've seen over the years. And, what then leads us today is the question of kind of, what's the limits of AI? How similar is what we're building today in computers to what's actually happening in human intelligence or natural intelligence? You know, what is it that we know about how we think, or how a monkey thinks, or how a dog thinks, or, you know, how a fish thinks, right? These different kinds of animal intelligence, how similar are they? You know, what is the way our brains process information about the world around us? How do we make decisions? How do we, you know, generate actions so that we can act on our decisions? I mean, these are still the things that, you know, we don't fully understand. And so, you know, the idea might be that we could even improve AI using facts about, you know, how we think. And so this is, you know, a very active area of research, and SueYeon is actually an expert in this area. She's, you know, even though she's young, she's had a lot of training and experience with this. So I'm going to let her explain a little bit about what we know about brains and their relationship to AI. All right, so let me stop my slides, and SueYeon, you can put yours up and talk.
Thank you, Dan. Let me start sharing my slide here. So can you see my screen? Okay, great. So yeah, thanks for having me. And I think that's a good place to talk about the connection between the latest AI models called deep learning and its connection to the brain. So deep learning it's different from other machine learning models and methods in that many of the building blocks are inspired by neuroscience. And what we call deep networks or neural networks, actually it starts from a model of a single neuron called a perceptron. Now, neurons, which are thought as basic building blocks in a nervous system, are connected by what's called synapses. And these neurons have activities called spikes, which are bursts of electric signals that transmit information between these neurons in the brain. And now we can go back to the perceptron in a neural network. And these perceptrons are single units in a deep network, which is one of the popular models in AI these days. And it operates by taking inputs from the activities in other units in this AI model, like the neurons in the brain. And it does the summation, it adds the activities from those neighboring units. And then these weights are basically like the synapses between neurons in the brain. And after linearly summing these neighboring units activities, then it goes through nonlinearity. And it's basically like how the neurons are transmitting information. And basically, this is very similar to how neurons function, and it's called integrate and fire neurons. And the output of this unit in an AI system is like a spiking activity in the neuron that we're looking at back to the biological brain system. And the network of these units are called neural networks. And having many layers of these units of artificial neurons are called deep networks. And the output of these networks, they are trained to emulate the task that a brain has to perform. And the success of a deep learning paradigm is mostly due to the success of the learning rule called gradient descent, which is implemented by a method called backpropagation in these artificial neural networks. And there are many similarities, but also major differences between the learning in the brain and deep networks. So the brain modifies the synapses to improve behavior, and so does deep learning models. So they are similar in that sense. However, implementation of these learning algorithms in deep learning models requires the synapses in many layers of this network to know all the connections from the particular layer in that unit all the way to the output, which is thought to be quite impossible in the real brain. So there are some differences still between these deep learning models and how they learn and how we think that the brain is actually learning. However, despite these differences, deep learning models have emerged as one of the most promising models for the brain. So then how are these deep neural networks related to the real brain beyond the initial inspirations, and how did these networks become so successful as a model of the brain? So the appreciation for deep network models for visual neuroscience really started in the human visual intelligence. So if you look at this picture, you might say there are cars or buildings or people and so on, but these are just pixels with numbers that the computers see. And the rest is understanding. Rest of the understanding is that the neural network's inferences about the external world. And what happens in the visual part of the real brain is that in the center of your eye, called retina, there is a highly sensitive region and a high resolution in the center of your gaze that you're looking at here. And the part of the brain that deals with object recognition is very connected to the central part of the retina. And your brain makes the analysis on the central fixation point as you're seeing this car. And here is an example. So I hope you're able to see the glimpse of what's in this image. And this allows to study the questions like, is there a car here? And this sort of task is what we'll refer to as an object recognition, which is one of the very common tasks solved by deep networks. And this is an example of a monkey doing the task that I just showed you, which then allows to study their biological brains while performing this kind of task. And these are the videos of monkeys in the lab of my collaborator, Jim DiCarlo, who's also generously shared many of the slides about their monkey work here. So then we're ready to talk about reverse engineering the brain with neural networks. Now you can take the brain and slice it and look at the layers and zoom in and look for the neurons and go all the way down to a single neuron and look at its activities. And we're going to go with a very common assumption in neuroscience that the spikes, which is what I just talked about, the bursts of electrical signals, those are what carries information in the real brain. And we're going to present the images of these objects just that we just talked about and then to the monkey. And measure these spiking activities from neurons responding to these images while the monkey is seeing these objects. And these are done in my experimental collaborators' labs. And then you can take the activities from different sites or different units, different neurons in the brain, and collect them and put them together. And you can record from hundreds of neurons from the area known to be responsible for object recognition in monkeys' visual area of the brain. And you can get these vectors of real neural activities responding to the images of objects. And that becomes a matrix of data with hundreds of neural responses for thousands of images. Then now we're ready to compare the brain's neural activities with deep neural networks trained to recognize objects with AI models. And then there followed a series of findings which shows that the activities of neurons in these AI models are actually well matched to the brain's neural activities, which leads to this interesting diagram where engineering progress in building better AI models ends up producing neural network models that end up being a good match for the patterns in real brain and finding a very good brain model. But the other way around also works very well. So for example, we can take this example where AI models are known to fail, called adversarial attack. So let's say we have a standard image, like a picture of a panda here, And both humans and artificial neural networks can recognize this as a panda pretty easily. But if you add a very small perturbation like this, and it's still very easy for us to see this as a panda, but the artificial neural networks thinks that it's a gibbon with a very high confidence. So this is a case where we see the divergence between deep networks, AI models, and humans, with humans performing way better than the networks. However, it turns out if you make the networks more like the real brain by adding properties from real neurons, like how they are tuned or their randomness, then it makes the network suddenly robust to these attacks, adversarial attacks. So these biological properties from the brain can also improve the engineering performance of AI models. And it's worth noting that it's probably because there's a shared goal between AI and deep learning and brain science, where in AI or deep learning, we want to build emergent models which can do intelligent things like tasks done by the human brain using simple building blocks like those perceptron units that I talked about. While in neuroscience, we want to understand how neurons work together to perform complex intelligent tasks. And if you understand it, you can probably build a model that's as good as a human brain. And by the way, we do a lot of work in this problem space, which is understanding the nature of computation in biological and artificial neural networks. And I hope I was able to convince you of the fruitful collaboration between the study of biological and artificial neural networks and the development of AI models, where the AI models can help us understand the brain better, and the inspirations from the brain can also help us build better AI models as well. And next, Dan will talk about the latest AI models and applications and see where the field is going.
Okay. Yeah, so let me spend I know we want to leave some time for discussion. So let me just spend a few more minutes just to introduce kind of some of the recent advances. So let me, hold on. Okay. Let's see. Let me go back. Okay. All right. So one thing I wanted to mention is, you know, recently, as SueYeon has been talking about, you know, neural networks and AI in terms of recognizing things. But recently, there's been very much excitement on what's called generative AI. And this is the fact that, you know, not only in our brains do we recognize the world, but we can also create, you know, new things, right? That we can, you know, write essays, we can draw pictures, we can, you know, make up new conversations. And this is now where AI is going, is in this field of generative AI. Maybe some of you heard about something called ChatGPT, which is the latest kind of language model that's been created. And so, you know, the excitement now is that AI has gone to a place where you can actually have ChatGPT be able to write, you know, a college level essay from scratch, you know, without, you know, by basically being able to reason about, you know, what words it should generate. But it can also generate things like programming, right? So, you know, instead of having humans program computers, maybe computers will start to program other computers. And then chatbots, right? Being able to have natural conversations, or being able to now what's called multimodal generative AIs to generate new images, right? So, you know, here's an example where you can take a AI model and say, draw me a photo, you know, make me a photograph of an astronaut riding a horse, and boom, this is what it generates for you. Okay, something that's never seen before, but you know, it's a fantasy, but it's able to create it. So that's the area of generative AI that's causing a lot of interest these days. And the way it works is, you know, these large neural networks, there's a new model, something called the transformer neural network that, you know, uses a selective attention to try to match different parts of sentences together or different parts of the image that, like SueYeon talked about, is like a foveated kind of attention. So what connects with what? And then you train these things, basically, you know, if you want to make a language model, you would train it by saying, fill in the blank. you would take a sentence, you remove a word and say, tell the neural network, try to replace the word, fill that blank in. And then if it gets it right, it gets rewarded. If it gets it wrong, then it tries to modify its weights using gradient descent to try to make it better. And then these things are trained on basically data from the whole internet. So it's a huge amount of data, right? Every possible essay and book or patent that's been published on the internet, you basically train these huge models using all that data. And that's why they're so good, is that it's able to basically, it's seen everything humans have made up until now, and it's learned these statistical properties using these transformer neural networks, and it's able to reason about, if you take out some part of these texts, it's able to fill them back in, or take out part of an image and it's able to fill it back in. So these are how these things are trained. And I'll skip some of this then. And then the idea is, how can you do this with robots? This is my field, is to try to apply AI for robotics. Things like autonomous driving that you've seen kind of people working on in terms of having machines be able to drive on the road. I had students working on things like having robots play soccer, on their own, or having robots interact with humans. So there's something called human-robot interaction interfaces. So these are important things where AI is very crucial to try to make. And from a consumer products point of view, right, AI can be embedded in many things that you have in the home. And this is, what some of my work at Samsung is for AI for a company like Samsung, is to think about where they should be embedded in different devices. So that's, all I wanted to kind of quickly go over. Let me stop my share. And so what we wanted to do now is maybe spend, 20, 25 minutes here in discussion. I see there's a lot of people online, so I can't see everyone at the same time. Maybe if you have a question, maybe it's easier to do it through chat. So why don't you, if you have a question, maybe you can type it on the chat channel, then I can take a look at those, and then we can have a discussion. Okay. So yeah, so if you have a question for any of us, please type that into the chat channel. And I can call on you if I need you to explain it better. But maybe while we're waiting for the chat. Okay, there's a bunch of questions coming in. All right. So Jian is asking, is there any other learning algorithms other than backpropagation? Maybe SueYeon, you want to explain, you explain backpropagation, what there are other forms of learning?
Yeah, this is a very good question. This is a very active area of research. So I think I showed two examples of learning. One was backprop, which is done very commonly in DeepNet. And I also showed Hebbian learning, which is one of the simplest forms of biological learning. But there's actually an array of biologically possible learning rules that people are trying to develop. The challenge here is getting the networks to learn with the learning rules that are similar to the brain while doing really well on performing complex tasks. It's a very challenging problem. So it's a very active area of research right now at the intersection between neuroscience and deep learning. So I highly encourage you to think about this.
Yep, great. And then I have another question. Samuel Choi is asking, with AI becoming more prevalent, this specialized ASICs being made for deep learning like Google's TPUs, do you see a boom for neural network chips like what GPUs did for graphical ASICs? Yeah, so the question is, chips, hardware chips for AI is definitely a hot area. As Samuel said, right now for a lot of these large scale, neural networks, we use GPUs to do, to speed up the kind of computation and training. However, if the power consumption that you need and the number of GPUs that you need to do this kind of training is enormous. If you estimate kind of the power cost to train, a large scale model like ChatGPT is actually very, very significant in terms of sustainability or money cost. So there are a lot of work, a lot of companies working on trying to build accelerated chips with maybe more specialized hardware that could be more like what the brain does in terms of the architecture. And so there's a lot of research on trying to make those kinds of chips. Another area that's very hot right now is to make chips more power efficient. So suppose you want to run a big neural network on your phone, right? On your phone device, right? How do you do that, right? You can't, you only have a limited amount of battery, but you do want your phone to have a better brain. So there are, neural processing units that people are making and trying to design and to fabricate that will then be embedded into a lot of these new devices. So it's a very big area of work in terms of hardware for machine learning and AI in the future. Okay. Let's see, another question. M. Kim, can we develop AI politicians if you think AI politicians would be better than humans? SueYeon, what do you think is the limit in terms of AI for things like
yeah, I'm not sure. Dan, would you vote for AI politician?
I know that they are working on AI for, like judges and stuff nowadays. This is actually a big area, right? Is this concern about, for instance, why are human politicians or judges maybe not so good? And that's because they're biased, right? They have their own kind of prior biases. They might be racist, sexist, they have these kind of biases. And so the thought is that maybe you could have AI be a more impartial judge or a kind of a more rational decision maker. But the fact is that AI can also be biased, right? So as we talked about, AI is trained on data. And if you actually give it data that's biased data, like for instance, conversations that are generated by humans that are not, that are biased or, trained on human provided content, then the AI will learn those biases as well. And so there's a big area of research now is to try to remove, how to guarantee that when you train a neural network that it won't be, under this influence of these bias types of things. So how do you remove the bias from these systems? So if you could do that, you might argue that AI would be a better rational decision maker or a better, than humans. But we're not at that point where we can guarantee that in any way right now. I know, SueYeon, what do you think?
Yeah, I mean, maybe I think you can ask ChatGPT to speak in the style of a politician. But yeah, I think using AI or bias or non-bias in AI to create like an archetype that is impartial is probably a beneficial way of using AI for things that relate to politics. I agree.
Yeah. So yeah, it's interesting to see how far we can take it, but I think there are some concerns about trying to do that right away. Okay, so we have a bunch of questions. So one is, can you provide some inspiration of the future applications of AI? So Hoon-Kyung was asking about some future applications. I think as we talked about, generative AI is a big area that people are saying whether you can use that for better search on the internet now or for content creation, right? You're talking about artists being able to use AI to kind of improve their their kind of abilities to make art now. That's a big area that people are thinking about, is that can AI help human creativity to some extent, right? To augment it, to kind of as a tool. So these are definitely hot areas of people that are trying to make startup companies and things like that in this area. Jiyeon is asking, is there any progress on using as little data as possible, just like how babies learn? So yeah, so SueYeon, you want to address the...
Oh yeah, so I think baby-like learning is also a very active area of research at the intersection between cognitive science and AI. And then people do things like mounting a video on the forehead of a baby in the first like 2-3 years of their life, and using those visual streams to train AI models as if they're like a baby. And I think it's a very active area of research. Dan, do you know any other examples of baby-like learning?
there's an area called reinforcement learning. So that's, definitely a hot area. One area of machine learning is to train systems more like what a baby or a baby animal might do. Is you reward it when it does something well, and you punish it when it doesn't, rather than trying to explicitly tell it what to do all the time. And so that's another big area of AI is to learn these systems that way. So let's see. Juno is asking, for a student who is studying art and design, could you recommend how a student should access AI for study, research, and application and practice? I think these days you can just download some apps and try it, right? There are a number of apps with that uses AI to do image editing. There are, like, for instance, I know definitely on the phone there are we have AI that is used for taking an image, and you can basically erase things. So like if you take a picture with your phone and someone is photobombing you, you can actually use AI to remove the photobombing, right? So there are things like that that's happening today. But with ChatGPT, you could try it out if you want to see how good the chatbot is. So yeah, you just give it a try. I think there's a lot of companies who are now providing these tools for general public, and so give it a try and see if you think it's good, or have suggestions for improvement. AI for home environments. Yeah, as we talked about, in robotics, there's definitely the idea of having a home robot. Let's see. Okay, Sungwon is asking, in practice, some people have an issue with explainability of deep neural networks, and some want to try explainable AI. Could you explain something about explainable AI? SueYeon, want to take that at all, about explainability in neural networks?
Yeah, so I think there's two types of explainability and interpretability. So for scientists, we're trying really hard to understand what gives rise to what. So going into the mechanisms of how, which areas or which building blocks are giving rise to certain types of behavior. But on the other hand, I think there's another domain of explainable AI, which has more to do with law and the things like that. And yeah, I think Dan, if you know also more about explainable AI in like a more applied context, I think this is also a very active area of research.
Yeah, so the idea of how can you build AI that people would trust better. So one idea is that instead of just giving you the output saying the neural network decided this or classified it, that it could try to using the language to explain why it came to that decision, right? That it's because it saw this feature in this corner, and then it was, its attention was then drawn to this part of the image, and that's why it thought it was a gibbon or whatever. So that's the type of thing that people are working on in terms of, being able to have the neural network in some sense analyze itself so that it can kind of figure out what features were the key features that generate the response. So those are the areas of research in explainability. Okay. So that's one. Let's see, we have a lot of questions. Okay. Another one. Dongyuel is asking, do you have any thought about uncertainty quantification, such as Bayesian deep learning? These days, large language models and generative AI is nice. Do you think about uncertainty? So yeah, so Dongyuel, you're mentioning Bayesian neural networks. So this is the idea of incorporating more probabilistic notions into neural networks. So, this is, again, another area of research is kind of how much do you need to be able to use probability theory to kind of either build into a neural network where it reasons about probabilities, or have a probabilistic analysis of these systems. SueYeon, I don't know if you want to talk about stochasticity in neural networks.
Yeah, right. In our brain, we have the neurons have randomness and built into the system. So we're actually, humans are very good at dealing with uncertain environment. So I think there's probably a lot of future progress direction in incorporating how to deal with uncertainty in the environment into the model, or if a model made some kind of decision, how much confidence should we give to the decision of a model? And I think that there's a very interesting problems to work on there.
Actually, this is one of the big mysteries in research, is that if you look at kind of the neural properties of a biological neuron, it seems to be, as SueYeon said, quite random, right? That, you know, there's a spike train that gets generated. It has very kind of large variance, Poisson statistics in some sense to the spike train. But, you know, using an assemblage of all these neurons, we are very well behaved in terms of we don't just do random things all the time. So it's kind of an interesting system architecture where you can use units, small units like these neurons that are have a lot of noise in them, but then using this noise properties somehow to be able to generate, you know, good actions and decisions. And that's much different than a computer, right? So if you look at kind of how a microprocessor is implementing a neural network, if you go in there and you delete some of the transistors, you're probably going to mess up the whole thing. So it's not as robust in a computer or a machine to some of these noisy properties or uncertainty that we're talking about. So this is still, I think, a big area is trying to understand, you know, right, SueYeon, how to understand what this what the stochasticity does for the brain processing.
Right.
Okay. Another Matthew John is asking, hello. As a recent college grad, I've been interested about learning about AI and applications to medicine like neurology and biomedical engineering. How would you recommend I approach that field? Maybe SueYeon, you can address.
Oh yeah, I think this is a very promising area. And I would say if you're interested in learning more about it, reach out to the labs that are developing these methods. I think there's a lot of research opportunities at the intersection between like medical imaging and using machine learning, automatically detecting like diseases and things like that. And I would say that's one way. There are probably a lot of, I think there are many startups that focus on these kind of topics, and maybe, yeah, look for the opportunities in both the private sector, startup, AI startups focusing on like, you know, using machine learning to medicine or academic labs. I think there's a lot of opportunities out there.
Mm-hmm. Yeah, so, you know, you should try it and then try to reach out to folks, you know, first nearby in your school that might have some expertise, or as SueYeon says, just to try to reach out and talk to people and try to get involved. Okay, so we have Jian asking about vision and natural have shown huge improvements, but emulating physical feelings, pressure, pain, touching sensation. And also M. Kim is asking, if AI is to mimic human intelligence, can it show emotions? Is it, you know, can it be programmed to mimic our feelings or develop emotions? So, yeah, so I guess, you know, there is this kind of big question is whether AI will ever be what we would call sentient. And there's been some debates about this. And, you know, part of being sentient might be that you have to have some emotional kind of response or and be able to react in terms of feelings. I don't know, SueYeon, do you know anything about how that works in our brains? First of all, the biological basis of emotions.
That's considered to be the area of the brain where we don't have access to unless it's called qualia, right? It's the subjective experience of something. Yeah, I think it's very interesting. I think how to quantify or even define an emotion in the brain or neural network models of the brain. I think I think it's a very interesting area. I haven't seen many research topics in that space actually.
Yeah, I think it's hard to make that a well-defined scientific question. Like, what would you measure and how would you measure it properly? That's what makes it hard to study scientifically. You know, from an AI perspective, people have, you know, made neural networks where you kind of, the human designer puts in, okay, this neuron is going to represent pain, or this neuron is going to represent happiness. And so in situations where it should be happy, this neuron, you know, will have higher activity. but it just put into the system. It's not really that the neural network is feeling happiness, right? It's just kind of mimicking it to some extent because the human put it into it. So it's not really properly doing what we imagine with emotions or feelings. And so this is definitely an area where we don't know how to build something like this, right? We don't even understand it, I think, well in the brain, and we don't know how to build it properly. So, and this is I mean, I don't know how many people ever watch Star Trek Next Generation, but this is a theme there. There's a robot called Data, and throughout the whole show, he could do, all sorts of computations and everything better than humans, except that he didn't have emotions. So he was always trying to learn how to make a joke or, understand, until he got this emotion chip, right? So that was also a theme in science fiction. So we're still at the point where we don't know anything about how to do that properly. All right. SueYeon, any comments more about emotions?
It's not my expertise area, but
Okay, someone asked, do you think Google publicized Bard too early with more time running? Okay, so I think it was yesterday where they tried to do a demo of Bard, and it made a mistake about the space telescope in terms of the facts about the space telescope. So yeah, so this is an area where you can see that if you train the system, maybe it was trained on articles written by humans that had that kind of incorrect knowledge in it. And for instance, if you train an AI on the current state of the internet, next year it's going to get facts wrong because things have changed and it hasn't been retrained yet. So these are all the things that you have to be wary about AI and understand its limitations. And so there's a lot of research in terms of trying to limit the AI so that it doesn't make these kind of incorrect inferences using old knowledge or things that humans have written that could be also incorrect or biased, right? This is again an issue of how do you prevent that? And that's a hard job, right? How to properly guarantee or validate that the answers that the AI gives are actually really correct. That's difficult to do. And I can see why that it was a mistake like that, because it's probably an article that said that somewhere that someone wrote that's not correct. Okay. John Park is asking, what are limitations of generative AI? For instance, can ChatGPT write a genuine research article, generating knowledge that was previously unknown, or is it just putting together what's been already known? Yeah, so definitely, creating things from scratch is difficult, right? Just like in scientific knowledge, it's hard to kind of come up with a new theory if no one's done that before. So ChatGPT and all these generative AI models are basically interpolating between what's been on the internet already. So it can kind of combine things together in interesting ways, but it's not really generating something completely from scratch that's never been seen before in the way that maybe a new artist would create a new genre of paintings that has never been done, right? So what ChatGPT or what Stable Diffusion models would do was take bits of Shakespeare and mix it with other authors and use those things and interpolate between them. Or in terms of this astronaut painting, right? He took a picture of an astronaut and knew what horses look like and kind of composed it together in a new way. So it's not coming up with completely novel things that humans have never done. So that's the limitation. Okay. SueYeon, any comments about that?
I sometimes feel like I'm a ChatGPT, like human version of ChatGPT, but yeah, but I do think that I guess it is interpolating, or at least the weights and synapses in these kind of models have been definitely learned from the examples, like a lot of data sets. So I think it's hard to define whether the outcome of ChatGPT is new or a hodgepodge of what's already out there.
Yeah, and you can, as you say, you can ask the opposite questions. How much human creativity is really novel? I think a lot of humans are just doing interpolation or replication or copying and pasting to a certain extent, right? So
yeah, as someone who studies the brain as a neural network, I feel like maybe I have a lot of components that are not incorporated into the ANN models yet, but a lot of the principles in my brain is probably very similar to these large neural network models.
Mhm. Yeah. Okay, and then Min Chung Kim was asking privacy ethics. Yeah, so these are all definitely concerns as well, right? With these systems is, there's already been some lawsuits now where people are suing these generative AI because they were trained on their, say their paintings, and they didn't get permission for these systems to kind of be trained on it and to generate things similar to what they have already created. So there's some lawsuits about, privacy or copyright violations or those kinds of things. Okay. Simon Shim is how and what do we have to do to educate our students about AI? Any recommendations? Well, you could take courses like, I don't know, SueYeon, you have any online courses that you
There are courses out there, Coursera and like open courseware, and it's very easy to teach yourself AI. I think it's one of the benefits of living in this age. Yeah. And then,
yeah, Hun Kyung is also asking about how to study. Yeah, so definitely there's a lot, these days with the internet, there's a lot of resources, online classes that are free, YouTube tutorials. So, if you look, there are lots of things online now. Or you could ask ChatGPT to try to teach you. That could be, that will definitely be, I think, a new area is to have AI be instructional tools, right? Where students can ask it questions and they'll try to answer them like a teacher would. Okay. Rosa Ungyung is asking, can AIs ask genuine questions? What's the mechanism behind AI's genuine questions instead of answering them? Yeah, so questions, right? Just to be able to definitely they do dialogue where if you start a conversation, they will ask you questions and you'll have a dialogue back and forth, just like human dialogue works, right? Like, hi, my name's Dan. Oh, what do you do? Do you find that fun? These are the types of things that they can generate because they're, again, kind of interpolating or mimicking kind of conversations that they've seen before. So that's how they're generating these questions, is that they're seeing the statistical properties of how humans would generate a question, say in a dialogue or conversation. But if you're asking, like, can it generate like a question that like, for instance, to define a scientific research problem, that would be harder for, I think, an AI to do, just like even for humans to do that properly. It's difficult. Okay. Another question about, okay, so John Sonu is asking about detecting whether ChatGPT is used. Yeah, so there's already been some work, I know, about people trying to build detectors so that, for instance, to check for cheating using ChatGPT. But it'll be difficult. I think there'll be an arms race, that it's in general hard to do it because these things are trained to basically mimic what humans have been doing. So, and sometimes the learning algorithm even has this kind of generative adversarial nature to it, where you generate something and you have another neural network try to figure out whether that's not human or human. And then the AI tries to say, oh, you were able to figure that out, then I have to change a little bit to be able to be more like human. And so you actually have this kind of whole protocol of training in AI sometimes where you have two AIs working kind of adversarially, where one AI is trying to detect whether the other AI is there or not. So that's kind of, actually an interesting training paradigm too. I know, SueYeon, you want comments?
Yeah, I was also thinking you could probably have a generative adversarial or adversarial protocol where as soon as there is a machine that figures out that something has been generated with ChatGPT, you could probably learn to just beat that. So I think it'll be very hard to detect it.
Mm-hmm. But you'll see, I think, tools coming online that will go into this area because it is such an important thing, and I think a lot of students do want to use it to try to make their lives easier. So Okay, I think we should try to wrap up. I know we're getting to 9:30. So Youngie, you wanted to run the last part of this?
Yes, it was amazing. Well, thank you, Professor Lee and Professor Chung, for today's quite inspiring presentations and conversations. And I also learned that, you know, this AI will teach us what human beings are. This is a new thing for me too. So there were some questions about online courses. In fact, we are planning to do that KSEA. Thanks to Dr. Benjamin Lee, we will have the Python instructional series on March 9th and 16th and 23rd. That's 3 evenings or Thursday. March 9th will the Python for absolute beginners. March 16th, Python for data science. March 23rd, we'll have Python for AI applications. So please join these sessions if you're interested in learning, really, you know, taking courses, and you will receive detailed information about this series. So in addition, we'll have a session celebrating Women in STEM on March 8th. This is an International Women's Day. And also the April's distinguished guest series will be on quantum science and technology. So now finally, it's time for an online raffle. Our IT manager, Joseph Kim, will help on this.